Hope you have had a chance to view my videos that introduce the fundamentals of chemistry. The most common batteries that may be found in the home are alkaline batteries. Alkaline batteries are dry cells. Dry cell batteries contain water, but the water is locked up in a viscous gel that does not slosh around. Alkaline batteries are not rechargeable and are usually thrown away once they have been depleted. The typical alkaline battery is built up in cylindrical layers as shown in the figure. The outermost layer is the paint or plastic wrapper. The steel casing is to protect the inner layers. The next inner layer is the manganese dioxide layer. This manganese dioxide is mixed with graphite for good conduction. The MnO2 takes part in the cathode reaction. Inside the manganese dioxide cathode material is a porous barrier that keeps the zinc anode separate from the manganese dioxide cathode. The porous barrier blocks the flow of electrons but allows the transfer of ions. The inside of the porous barrier is coated with a gel of alkaline material that promotes ion flow. The alkaline electrolyte is usually potassium hydroxide KOH. Sodium hydroxide NaOH could also serve as the alkaline electrolyte. Inside the porous separator and electrolyte is zinc powder mixed with gel. The zinc is part of the anode half-cell reaction. The zinc casing is connected directly to the anode terminal or negative terminal of the battery. Embedded in the zinc anode center is a metal pin which is the current pickup for the negative terminal. Note, the negative terminal is isolated from the steel outer casing by a plastic protective cap. The open circuit voltage between the anode and the cathode terminals is 1.5 volts. When the circuit is closed, the electrons flow from anode to cathode. In operation, the zinc in the anode bonds with the hydroxide and water that is carried through the porous electrolyte from the cathode half-cell. The anode half-cell reaction is zinc plus 2 hydroxides plus 2 waters reacts to form zinc hydroxide plus 2 waters plus 2 electrons. The 2 electrons produced in the anode leave the negative terminal, travel the circuit, and enter the positive terminal into the cathode. In the cathode, the 2 electrons cause the 2 manganese dioxides to react into a single manganese trioxide and release a single oxygen ion. The free oxygen ions bonds with a water molecule which immediately splits into 2 hydroxide ions. The net cathode reaction is shown. The cathode reaction is balanced with respect to elements and charge. The 2 hydroxide ions migrate across the electrolyte with the water molecule to the anode half-cell and start another anode half-cell reaction with the zinc. The reaction continues as long as the circuit is closed and the zinc anode and the manganese dioxide cathode are available to react. Once the zinc is depleted, or most or all of the manganese dioxide is converted to manganese trioxide, the reaction stops and the alkaline battery is dead. Another common type of dry cell or solid-state battery is the lithium-ion battery found in cell phones and laptop computers. A major difference of lithium-ion batteries from other batteries is that lithium-ion batteries require charging before first use. The other batteries we have looked at, lead-acid and alkaline batteries, start out with fully charged anode chemicals and are ready to go. Lithium-ion batteries start out with an uncharged anode and must be charged before they can operate. Early experiments with lithium-ion batteries began in 1976. Stanley Whittingham made a lithium-ion battery with a lithium-titanium disulfide cathode. In 1979, John Goodenough built a battery with lithium cobalt dioxide. Development continued through the 1980s. In 1985, Akira Yoshino developed a prototype lithium-ion battery. In 1991, under a team led by Yoshio Nishi, the Sony Corporation made lithium-ion batteries available for commercial use in its Sony Walkman. The great thing about lithium-ion batteries is that they are rechargeable and have a reasonable high energy density compared to other batteries. Where a lead-acid car battery can store at most 40 watt-hours per kilogram, most modern lithium-ion batteries can store up to 250 watt-hours per kilogram or 0.9 million joules per kilogram. The energy storage capacity of lithium-ion batteries is still low compared with fossil fuels. Gasoline can store 13,000 watt-hours per kilogram, or 46.7 million joules per kilogram. This is more than 50 times the energy density of lithium-ion batteries. Another downside of lithium-ion batteries is that they are built with flammable components that can catch fire if overcharged. Lithium-ion batteries have some record of spontaneous combustion in aircraft, electric cars, toys, and certain cell phones. There are many types of batteries in the lithium-ion battery family. I'll focus on the lithium cobalt oxide, or LCO battery, and how it operates first, and then touch on other lithium battery types later. The LCO battery anode material is a layered graphite matrix. Graphite is just a form of carbon. Upon charging, the anode matrix traps lithium ions and electrons as lithium carbon-6. The trapping of other atoms between layers of graphite is called intercalation. The anode end caps are copper. The LCO cathode material is lithium cobalt dioxide. The cobalt is in its cobalt-3 valence electron configuration, CO3+. The cathode material can use a polymer binder such as PVDF, polyvinylidene difluoride. The cathode end caps are aluminum. Lithium-ion batteries use different electrolytes. Handheld devices use solid polymer electrolyte. One common polymer electrolyte is the polyvinylidene difluoride. Most lithium-ion batteries use a polymer plastic separator. The electrolyte is embedded in the separator matrix. Once the components of the LCO battery are assembled, the first step in making the LCO battery operational is to connect the DC charger. The figure diagrams the components of the LCO battery in its charging state. The DC charger forces electrons out of the LCO cathode terminal and into the anode terminal. The loss of cathode electrons breaks the bonds of the lithium from the cobalt oxide, leaving free Li+ ions. The charging causes the cobalt to enter its CO4+ valency state to maintain its double bonds with the oxygen. The charging cathode half-cell reaction is shown. The electrons move from the cathode through the DC charger and into the anode. The increase in negative charge in the anode graphite matrix attracts Li+ ions. These positive lithium ions from the cathode travel across the separator and into the anode. The charging anode half-cell reaction is shown. The lithium ions react with the graphite and the electrons to form lithium carbon-6. The charger must have a smart sensor to prevent overcharging. The voltage across an LCO battery is usually less than 4.2 volts. If the charging exceeds 5 volts and the anode spaces become filled with lithium, or if the battery temperatures exceed 130 degrees Celsius, the cobalt oxide could release oxygen. The free oxygen could begin a combustion reaction with the flammable electrolyte and cause a fire. The figure diagrams the components of the lithium cobalt oxide battery in the charging state. The Li+ ions are leaving the cobalt oxide cathode to fill the graphite anode. Once disconnected from the DC charger, if left alone with the switch off, the LCO battery will discharge slowly over a period of days or months. If the switch is turned on, the discharge of electrons from the anode or negative terminal begins. The electrons pass through the wire in the device shown as a light bulb in the figure. They return back into the cathode through the positive terminal. In the anode, lithium+ ions split from the lithium carbon-6 in the graphite matrix, leaving an electron free to travel through the wire. The separator blocks the electrons from taking a short circuit straight into the cathode. The discharging anode half-cell reaction is shown. The lithium carbon-6 becomes graphite plus a positive lithium ion plus an electron. The anode pumps electrons into the wire. The positive lithium ions migrate from the anode through the electrolyte and the separator into the cathode material. The electrons in the wire enter the cathode through the positive terminal. The incoming electrons react with the cathode material. The electrons in the lithium ions bond with the cobalt dioxide to form lithium cobalt dioxide. The cathode half-cell reaction is shown. The reaction continues until the switch is turned off or the graphite anode is emptied of lithium ions. A brand new, fully charged LCO battery can discharge at 4 volts for 8 to 12 hours. As the LCO battery gets older and has gone through several hundred charging cycles, the amount of charge it can hold degrades, so its charging time decreases until it is useless. An LCO battery should be replaced well before it gets too old and useless. Recharging when the charge falls below 40% is better for cycle life than allowing the lithium-ion battery charge to fall to zero. There are many reasons why an LCO battery degrades over time and discharge cycles. One reason is because during charging, lithium will react with the electrolyte and create unwanted compounds. These compounds are called solid electrolyte interphase, or SEI layers. These SEI layers deposit on the electrolyte or in the graphite anode. These SEI layers reduce the storage space for lithium ions in the graphite layer, as well as reducing the total number of lithium available for carrying out charging and discharging operations. A second major reason for loss of capacity in LCO batteries is the formation of cobalt-2 oxide in the cathode. Unlike lithium cobalt dioxide or cobalt-4 dioxide, which readily take part in the charging and discharging process, cobalt-2 oxide does not take part in the lithium-ion exchange. Cobalt-2 oxide is extremely stable. The cobalt-2 stays locked to the single oxygen and will not bond with the lithium. A buildup of cobalt-2 oxide in the cathode will severely reduce the charge capacity of the LCO battery. There are many other forms of LCO degradation that reduce the LCO battery lifespan. Similar problems reduce the lifespan of other batteries in the lithium-ion battery family to a greater or less degree depending on the battery component materials. Although cobalt is the favored cathode material for lithium-ion batteries, manganese-based cathodes are more desirable because manganese is more plentiful and less expensive than cobalt. Manganese-based batteries have less energy density than cobalt-based batteries. Often, the less expensive manganese-based cathodes are doped with cobalt to improve energy density while keeping material costs down. Materials that have been used in cathodes of lithium-ion batteries include LiMn2O4, used to create LMO batteries, LiNiCoAlO2 has been used to create NCA batteries, LiNiXMnyCO2O2 has been used to create NMC batteries, and LiFePO4 has been used to create LFP batteries. NMC batteries are the most popular type of lithium-ion batteries as of 2020. The traditional material used for anodes in lithium-ion batteries has been graphite. Other anode materials for lithium-ion batteries include layered silicone and hard carbon. Lithium titanate, Li4Ti5O12, has been used in the anodes of LTO batteries. A tin cobalt alloy has been used in Sony's Nexel ion battery. The replacement of traditional graphite anodes with more advanced anode technology is thought to be the next step in increasing the energy density of lithium-ion batteries. What makes the cobalt material of the lithium-ion battery somewhat complicated is that cobalt is a transition metal. And although we are taught the octet rule in chemistry basics, that the valence electrons only come from the s and p orbitals, in the case of transition metals such as cobalt, the d orbital electrons can and do participate in bonding. So, while we would expect from its position in the periodic table that cobalt would want to give up its 2s electrons, and that it would have a cobalt-2 valency, CO2+, the fact is that cobalt-3 and even cobalt-4 exist when the d orbitals contribute to the cobalt valence states. Cobalt-3 exists in the CO3+ valence state in the cathode compound LiCO02. Cobalt-4 exists in the CO4+ valence state in the cathode compound CO02. Lithium-ion batteries use different electrolytes. Some lithium batteries use hexafluorophosphate, Pf6- ions, in a dimethyl carbonate solution in their electrolyte. Handheld devices tend to use solid polymer electrolyte, SPE. Some SPE polymers that are used include PVDF, or polyvinylidene difluoride. PAN is polyacrylonitrile. PMMA is polymethyl methacrylate. And PEG is polyethylene glycol. Advances in lithium-ion batteries continue to this day. For the near future, lithium-ion batteries will be the battery of choice for both handheld devices and for electric vehicles, where the need for a portable, rechargeable source of energy is required. While batteries are king when it comes to handheld devices, the low power density of batteries compared to fossil fuels will remain a challenge to electric vehicle manufacturers. The solution to mid-size energy storage may be fuel cells. I will discuss fuel cells in my next video. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.